folks, how are you? Oh, it's Brian again in Denver, and he's doing these damn peak things again. Here we go. This guy's got it bad for this stupid proof. Yeah, I wanted to go back. How you doing? I hope you're all well. Thanks for joining me. I'm trying to make this quick. Got a lot of stuff to go through. Kind of revisiting this shot that I did a video on about a month ago, and then I did another video where I used some photos from hikers because this is an aerial shot. So, we didn't know where our height of the observer was. Excuse me, but anyway, this is an aerial shot about 33 miles from Pikes Peak, 67 miles from Crestone Peak, which we can see sitting up over top of Pikes here. So we're trying to get this fourth saline, kind of mountains of evidence type proof here going on. And yeah, I don't know exactly where the observer height is. So we're going to figure out, I figured out how high it has to be. And I actually emailed and contacted this photographer guy, the guy who took this picture. And we went back and forth. He was a super nice guy. And asked him about, how do you know exactly where you were? Because he did, say in the book, his book with this photo and on the website that it was at 14,000 feet, even. But anyway, so I wanted to get in contact with him and see if he had any documentation on exactly where he was, a flight log or something. And we went back and forth, and I'll talk about that. And I did another video where I used some hikers, photos from tops of peaks from top of Mount Snowmass, and was making claims about, I don't think we should be able to see this, and I don't think we should be able to see that. And somebody came along and said, well, let's, prove it. Let's do the math and figure this out. And he was kind of a, a skeptic, but really nice guy. And so we went through and kind of used the Metabunk methodology that they used on that Mountain of Evidence, the Blue Ridge Mountain video. And we're dealing with, shorter distances in that video. And that's what, I kind of like that video, and I think this is a really cool way to do it. And the guy who was actually, kind of challenged me and we went through all the math was like, yeah, actually this is a cool way to kind of, observe and or map out curvature or no curvature, or what can we see or what shouldn't we be able to see. So it's, we're kind of forcing the line between observer, a midway point, or this thing is like a third way of there, and then a final target, forcing a line across 3 points. Do they line up or don't they? Is it on a ball or not? So hopefully you understand that by now. I know I just got a comment on this video that I did a month ago saying, well, height of the observer, use the calculator. And we're trying to bypass that stupid calculator. So please don't tell me about the height of the observer calculator. I'll show you why. We'll go through this, but anyway, sorry about that. A little sensitive. Got a lot of comments like that. But it's true. The height of the observer is very important. As I found out, when we did the math on that last video from the shot from Snowmass Mountain looking out. And I'd done another video really quick because I thought I had found Evans Mountains, or Mount Evans, which was like a 100-mile shot. But I didn't. I hadn't found it. I was mistaken. And Rory, this guy, came back and he checked it out and was like, nope, you blew it. That's not Mount Evans. And it wasn't after I went back and double checked. So I had to pull the video down. So Rory's got 2 and I've got 0 so far. So anyway, but I mean, it was great because it kind of made me do this math and kind of figure out what you can see and what you shouldn't be able to see. And it's pretty amazing, even at really long distances, 60, 70 miles, how slight our viewing angles are. We're talking about tenths of a degree, hundredths of a degree this way or that way. So it gets tricky. You need a really long, super tight line. And, I'm still going to be searching and maybe going for some hikes this summer and map some things out and take some of my own photographs from the ground where I know where I'm at, and maybe do another one. But I kind of went back. I wanted to go back to this photo because it's pretty awesome the way we got Crestone here over Pikes. And this guy claimed it's at 14,000 feet. So yeah, so I emailed this guy. Let me show you his book. You can download his book for free. And it's got like 600 aerial photographs in it. It's crazy. So this is the photograph that we're looking at here. So he did this panorama of the Front Range, and it says here on this photograph, which was one of the only photographs in the book that actually, where he says the altitude of where it was taken. And he says in the book, as well as on the website, this view is made from an altitude of 14,000 feet, 5 miles east of Larkspur, Colorado. So that's why I emailed him and said, I kind of said, I'm kind of studying how to triangulate the camera position and the 2D image and all this stuff. And I really like this photo. It's very challenging. Are you sure it's at 14,000 feet? How sure are you, and how do you know that? So just take a look down here at our foreground. This is Colorado Springs, basically down this way, and the Air Force Academy and things over here. But an I-25 running along here. So I did some overlays. I took some of the photos and overlaid them onto Google Earth. Well, we'll take a look at that just for fun. I don't know what it proves or doesn't, but Rory, the guy who was commenting on the other video, he's like, yeah, lay those pictures on Google Earth and just, play with it, see what happens. So I did. That was kind of funny. I don't know. It's kind of funky to try to lay a 2D image onto, especially from this perspective, where you're not looking straight down at the ground or something. But anyway, let me keep going here. So yeah, I emailed this guy, this photographer, and he said, so yeah, he came back to me, and he said, well, it's a really good guess, and he actually sent me this photograph. And he cropped it right here and said, see how Crestone and Pikes Peak, or how these peaks are all lined up with Pikes? We must be at like 14,000 feet, right? Because it's all lined up. And it's funny how people never account for the curve, right? So it's like, yeah. And so I wrote him back and thank you for responding. And I was like, yeah, that's kind of the part of this picture I'm really interested in myself. And here's why. Because here's some curvature numbers, and Crestone Peak I don't think should be able to be visible. If you're at 14,000 feet or somewhere even with Pikes, then Crestone should drop down at 100 miles away, and you shouldn't be able to see it. And I kind of gave him some numbers and the 8 inches per mile squared formula and stuff like that. And he came back and said, well, I think the world's curved, but I don't know where you're getting this math, and 8 inches per mile squared doesn't seem right to me. Where are you getting that? And all this stuff. And so he's like, I agree that maybe I am higher than 14, maybe 14.5 at the most, is what he said. And I said, okay, well, and then I sent him the a copy of the curvature, the chart that we've all seen a million times, the 8 inches per mile squared, and said, yeah, this is widely accepted within, a couple hundred miles as being pretty accurate enough. And, this is where my numbers are and the angles to the peaks from the observer. If you were at 14.5 or whatever, I said, even at 14.5, you shouldn't be able to see it. I think it's more like 15.5 or more, and it's actually more than that. What are you doing, Wilson? My dog's slinking in. Hey, what you got? So yeah, and he's like, oh, that's very interesting. After I sent him the curvature math, and he kind of sent me back a diagram that he made and was like, yeah, we could figure that Pikes Peak goes up, right? And the other two, kind of the hump theory versus the drop theory. And I wrote him back and said, yeah, that's another way to look at it. Things kind of work out the same. You either get angles that are positive or negative, from point A to C. So point A is going to be us, our camera. Point B is Pikes Peak. Point C is Crestone. And so he's like, oh, that's interesting. So then he had a friend of his who's a mathematician draw it up and figure it out, what the height of the observer would have to be on the ball, and we'll talk about that, and I'll show you that. And I was like, oh, that's cool. And I haven't written him back, even though his friend kind of fudged the numbers. He took about, he's like Polish dude, and he did it in kilometers, but he took about 50 kilometers off our total distance. He like totally lowballed the numbers on our distances and came up with 14,880 feet for our height of our camera here. Let's see here. Let's see if we can scroll through these guys. So this is our foreground shot. This is I-25. This is all of that same photograph. He took the 8 photos that he took of the panorama and then put them together and broke them up into 30 different frames on the high def thing, so you can choose between 30 different frames within that panorama shot all up and down the Front Range. So this is the foreground of that. That's I-25. Again, this is Colorado Springs Air Force Academy kind of area. So just kind of think about that. We'll take a look at that. Here's some math that I did. Come on, buddy. Please move. Man, everything moves so slow. And this is the math as Buddy did. And we'll look at that. What do I want to do here? Let's go. Let's go. So anyway, let's give Rory some credit. This guy who, on this Flat Earth Colorado is Flat video, we got into this pretty long thread, which is really awesome. So he gives the link to the Metabunk Debunked Blue Ridge Mountains Impossible on Spherical Earth video. You can check that out. So we went back and forth. And he was really cool. He did all this... I was trying to give him the exact coordinates of the photo. This is not the photo we're talking about in this video, but the previous one from Snowmass Mountain. So he did all the math on what I was looking at, looking at Mount Princeton and Yale over these ridges and all these things. So we get positive angles here on this stuff. Ridges are lower than our peaks. But we can see more of the mountains than just the peaks, but it's kind of an issue of how much of those mountains should we be able to see in that photograph. But it's hard to do. Like I said, I went out and kind of looked at some stuff as far as like the lowest points on the horizon that we could see over ridges and peaks. And even then it gets tricky. I mean, you're hundredths of a degree this way or that way at certain distances. That's why we really got to stretch this out to like 80 to 100 miles. But he was really cool. Please do check my figures if you're in agreement. I checked all his figures. He says, wow, that's cool. Thanks a lot for doing that. I kind of claim here that I found Mount Evans over Crystal Peak, which I did not. He's like, wow, if you did find that, then that would be it. You nailed it. But I didn't. So we went back and forth about that video, and I basically said, yeah, I had to pull it down because you were right. I blew it. It was close. It was really weird. I mean, it was like the mountains almost, the profiles and stuff looked exactly the same. But anyway, I blew it. So I said, yep, I pulled it down. You win again. And he says, thanks for posting the comment and for everything else. When I get a bit of time, we'll be looking at your original photo in greater detail and seeing exactly what it's telling us. The technique still works, and I believe it does. And so I think that's about how far John McIntyre was out of. Anyway, sorry. So yeah, he says we should go back and look. So he was a super nice guy on that video. Check out that video. Check out these comments. Thanks, Rory, for holding my feet to the fire and making me not be so lazy, because I was totally lazy, as in this video as well, because I just kind of guessed it. And I said, I don't know. I think the plane has to be at least 1,000 or at least 2,000 feet higher to see Crestone Peak, but I didn't figure it out. So. Okay, back to this photographer and his friend, his Polish friend, who's a mathematician who did this. Can you see this? It's a little too big, right? Pull that back a little bit. Sorry, come on. My computer is so slow. I apologize. So this is A is our camera, B is our Pikes Peak, C is Crestone. These lines are our radius of our ball, Earth, plus the altitude of the mountains. And so he's figuring out, the cosine, the sines here of these angles, and then using the ratio to find the length of A, right? Pretty cool way to do it. You can redo this yourself. It's a little different than how Rory and I were doing it. Please move. I mean, it's just ridiculous. My computer is so bogged down. Sorry. So he's saying T is 30 kilometers. Please move. Which is camera to Pikes Peak, and Z is 80 kilometers, but he's off. I mean, he's way off. It's more like 52 kilometers here, and it's 107 kilometers from Pikes Peak to Crestone. I mean, you can just map that out. So he's lowballing these numbers, but I'm not arguing the math at all. This is all kind of in Polish, but he's coming up with A as 4537 meters, which is, like I said, 14,880 feet. For that length, as far as our height of the observer above mean sea level, right? Because we're doing this is all these altitudes on the peaks are measured above mean sea level, which follows a curve, so it has to. So that's what we're trying to figure out. Okay, please just move. computer. So there's that guy. So you can check that out and redo it that way if you want with different measurements. So let's go back. So here's my guy. Oh, come on. I mean, what? It's just a stupid sketch here, people. I apologize. Please move. I don't know why it takes so long to move a picture. So here's our deal. So this is how we do it. The Metabunk way, which is we take our height of the observer, we take a horizontal line, a fictional horizontal line 90 degrees to our radius, right? And then we measure our angles down with the drop to our targets. And then we're trying to get an angle where the observer is up to a height where the angle to the first obstruction, Pikes Peak, is lower than our angle to Crestone Peak. If that makes sense. So yeah, we got our horizontal line, and then these dotted lines represent, say this is kind of a top here of our chart. Our 0.23 angled line was right here to the Pikes Peak, and then our 0.702 is our dotted angled line down through Pikes Peak to Crestone. So our angle to Crestone's bigger off of our, it's larger off of our horizontal tangent perpendicular to our observer than our angle to Pikes, right? So we have to figure out how high we need to get this camera up to go from a negative to a positive to where our angle to Pikes Peak is greater than our angle to Crestone, which is down here. And basically I needed to put it up to about 16,300 feet to get that to work. So what we have here is we have our mileage and our distance in feet, 174,240 feet to Pikes Peak, 300,000, so 67 miles. So 100 miles, we did the total distance. I didn't write it on there, but it's, 528,000 feet, right? 5280 times 100. So that's for that distances. So that gives us our triangle leg. So we just use a triangle calculator and punch in those numbers. And then this number here that we're calculating is our short side of the triangle, which we are trying to calculate the opposite angle from, which is over here. Correct? So we go camera minus the elevation of our peak plus the drop for curvature, our 8 inches per mile squared drop. So here we got Pikes Peak at, I started at the same as Pikes Peak, 14,110 feet. So we take off the altitude of Pikes Peak, which gives us 0, and then we add our drop, which is 726 feet per 33 miles, and that gives us that leg here of our triangle above. Crestone Peak, we do the same. We take our camera, we subtract 294, which we end up still with a positive number, and then we take off another, negative number, and then we take off we add our 6,666 feet for a 100-mile deal, and we're at 6472, so that becomes this leg of our triangle, correct? So these gives us our angles if we do that into a calculator. I put the 90 degree up top here. I don't know, I was like, maybe I should have put it down here, and that would kind of account for our tilt, as our degree, our ball tilt of our radiuses. But I mean, the difference was so negligible. I tried it after I did all this, and it was like barely any difference in our angle, just like hundredths or thousandths of a degree. So anyway, I left it like this. So this is how I did it. Cool, does that make sense? So if we raise our camera, then these numbers go up, right? So we go to 1516. If we go to 14,900, which is kind of just rounding up of what the math that our guy did, our photographer's friend did, and even at that we're negative almost 3/10 of a degree, and that's the thing. I mean, we're dealing with these really low numbers and degrees. It's pretty amazing. So it's been kind of it's a good eye-opening experience to look at this, because a lot of times, there are a lot of videos or people say, well, look at that, and as I did, and say, looks flat to me. And it's like, well, is it flat? How flat is it? Do the measurements and figure it out. And it's a big ball. If we're on a ball, yeah, it's a big one. So it's pretty darn flat. But there is a curve. There has to be a curve. So let's measure it. So I put up here at 15.5, kind of my guess. I did some quick calculations. I was wrong about that. I was underestimating, which we're still at negative, but we're getting closer. You can see our numbers here are getting closer, and so I was like, okay, well, finally got up to 16.3. I kind of kept adding and adding and adding until I finally got a positive number where our angle to Pikes was greater than our angle to Crestone. Makes sense? So that's how that is done. We'll go back and look at that, but so here's our foreground of our photograph. Here's this guy. So I laid these on Google Earth. Let's go look at Google Earth real quick. Try to do this quickly. I know I hate Google Earth. So this yellow line is our shot from our plane over Pikes Peak to Crestone Peak, way out here in the distance. That's what we're looking at, this line, this ridge line. I mean, in this photograph, he actually has State Line Peak marked, and it's 160 miles away, and you can see it. But interesting enough, there's nothing in the foreground that would stop you if we applied that same methodology that I just showed you in my scribbles to this. Actually, we still get a positive number for something 160 miles away if we're at over 14,000 feet here. So, you know, just because you see something 160 miles away, yes, I understand that height of the observer is important. But if we force something or force a line in between it, then, oh, come on, please. Then we kind of force the line with our Pikes Peak in the middle of it. So if we had something, you know, a little taller or equal to the same height as State Line Peak out there right in the way, we could probably try to figure it out. But I did a quick calculation on it, and I was like, well, it actually, you know, like over this ridge here or something, it should still be visible on a ball from our height. So I get it, but please, please leave me alone about that damn calculator. So I put some pictures on here. So we'll take a look. This is our foreground overlay down here, and this is our Pikes Peak overlay. I don't know what this kind of, oh please, it's not going to work. I'm not going to, okay, thank you. My mouse is dying. I've been doing this too much. Navigating stupid Google Earth. Oh, please go down. So we're at 14.117 here, so this is pretty good. Okay. This is so nerve-wracking to try to get this done in a decent amount of time, so I appreciate you sticking with me. Oh, come on. Get info. We'll kind of fade this in and out. So I overlaid this photo. And it's hard to tell, so here's the photograph. And if we drop it back, I actually got pretty lucky on getting this laid on here pretty and sizing it right. But you can see, you know, this face and these peaks in the foreground here and either side line up pretty good. I mean, things in the background here, kind of the two-dimensional photograph kind of lays down on top of Google Earth, and so you kind of lose some of the ridges and peaks directly behind Pikes Peak here, as far as from our angle, what we're looking at it here. But we take it back to Google Earth, and we take it back in. So we're at 14.171 I elevation on Google Earth looking at this. Please move. And we bring our photo back in. So it's kind of cool. We got a snowy picture on top. And just kind of all the little cracks and crevices actually line up pretty good. But again, I don't know. I mean, we're looking at this. There's some things where it just doesn't match up. So here we are at 23,000 feet. We are at 15, sorry, 14.6, 16.1. It's hard to say what this tells us. But it was a cool exercise to do. So it looks like things, I mean, we're definitely looking at things pretty straight on, you know. So here's kind of our photograph. Let's get down here to more of a elevation closer to what we are. So here's our overlay of our foreground, our I-25. We're at 14.6 here, foreground. Get info. Let's bring this in and out. So here's our Google Earth. Here's our photograph. Google Earth, you can see things moving. It's funny how. So I was kind of concentrating on this I-25. And these roads in here, this interchange, trying to get it to line up. So our photograph, we kind of got our little lake down in here and our ravine and our ridges. The streets are actually kind of different along here. It's kind of strange, but it could be a Mandela effect. There's our photograph. And here's Google Earth from 14,911 feet is our eye altitude. I mean, you got to stretch these out and try to make everything match. So I think we're dealing with such a scale here that if you really try to use the photograph to kind of figure it out where we are, I think it would be a technical question that would be pretty involved. And I kind of looked up some things about how to do that, and it is pretty involved. Focal lengths and all the kinds of things. So somebody else could do that. But anyway, it was fun to kind of mess with it. So let's get out of Google Earth. All right? Please. So yeah, come on. So essentially, here we are at 14.4. It's kind of our photograph. So you can kind of see that angle, what it looks like on the Google Earth issue, and then what it looks like from our photograph, full photograph. I mean, it looks lower. I mean, you look like you're looking more at a 90-degree angle towards Pikes Peak and these faces of these ridges, and everything's pretty flat. You know, to me, it looks like he's at 14,000 feet or so. But maybe somebody out there who's a pilot might have a better inkling. So anyway, this isn't about proving, because we just don't know. Like I said, he said it's a good guess because we're all lined up. Then I said, you are assuming the world is flat. So this is our foreground again. Let's go to our guy here. So yeah, I could show you this whole, oh man, this thing is running long. So that's the math I did. Somebody just left me a comment saying, why don't you show me your math, dummy? And you know, of course, about the height of the observer. If you're at 14,000 feet, then there's no reason you can't see 100 miles. And it's like, yeah, as long as there's not something in front of you that's also 14,000 feet. And that's the whole point to this. So here's the panorama, his website. So go check this out. For $40, you can get this whole panorama, high def. I think I'm going to buy it from him. He's a super nice guy. And he, you know, maybe I got him thinking and scratching his head, but you can see how this is 8 photos turned into 30 different panels. This is our foreground. So this is that whole shot we're looking at. So yeah, I'll show you actually. So this is State Line Peak. That's the one that's 160 miles away, supposedly. Yeah, and there's a ridge right there. I mean, I actually kind of measured out to that ridge and to State Line, and it's funny. Yeah, it's not that you shouldn't be able to see State Line Peak, at least the very top of it. It's kind of how much of it should we see, but that's a 3.2 mile drop at 160 miles. So anyway, so here's that whole panorama shot. Pretty cool. Let's take that down. Let's go back to here and let's end this thing. I appreciate you sticking with me. I finally wanted to do this math. This one's for you, Rory, and everyone else who Do you see what we're doing here? I hope this makes sense. It finally made sense to me. And so I did all this math. And yeah, it's tough to... This is not easy because we're dealing with very small angles, degrees here. Fractions of degrees, even at 100 miles. But, like I said, I came up with 16,300 in order to get to our positive number, our height of the observer, to see over Pikes Peak and get Crestone above it. So let me know what you think. I appreciate you sticking with me. Finally did some math on this, and hopefully that'll satisfy some people. I'm not saying that the photo is a proof, because we don't know. You know, like I said, I contacted the photographer and he said it's a good guess, and he didn't come up with any, you know, he gave us his buddy's math here, which you can check out and do it this way. It's a pretty cool way to do it. But like I said, he totally lowballed those numbers. So, you know, Please move. Okay, I really appreciate you sticking with me. Come on. Come on, come on, come on, come on. Please, computer. Just go back. Oh, computers. Gotta love them. Saturday morning, having coffee. Thanks for sticking with me. Let me know what you think. I gave you some numbers on this thing. So he says it was at 14.5, 14.8. I say it has to be at 16.3, another 2,000 miles, which was kind of what I guessed in the original video, but I didn't actually run the numbers. So here we do. I ran the numbers for you. Let me know what you think. I appreciate your time. Thank you. Peace.